Yeah, so I did want to give a little shout out to my book. Much, but not all of what I'll be presenting in these lectures are in the book. It's intended to be a somewhat pedagogical presentation. And I have a copy of my slides here, and I'll put it up again at the end in case you want to download the PDF and follow along or catch up on something that you missed. So let's see. This should forward the slides. Okay, so this is more or less what I want to do, talk about a very elementary introduction to Berry phases and curvatures. I guess somebody has to do that. And then I'll talk about these things today, and then tomorrow, as I said, will be more about Wannier functions, electric polarization, and so on. So let's get started. Okay, so what is a Berry phase? Many of you know, but in case you don't, here's an introduction. You imagine that you have some sequence of states, U1 up to UN, but UN and U1 are identical, so it's a closed loop. And here I've done it for a discrete set of states. These are vectors in some complex vector space in complete generality, but let's imagine that they're the ground state of some molecule, and I'm undergoing some path where I vary the coordinates of the atoms in the molecule around some closed path. And I calculate this product of inner products of the ground states of the molecule, U1 with U2, and then U2 with U3, and so on. And I go all the way around the loop, and I take the imaginary part of the log. That's the argument, that's the complex argument of the result. And the reason why this is an interesting phase is because it's invariant with respect to the individual phases of the individual states. So for example, if I take U2 and replace it by e to the I beta times U2, so this is some phase in front of it. This is called a gauge change in this context. So the gauge change has no effect on phi because U2 appears once in a bra and once in a ket, and the phases cancel out. So this is a global phase that's invariant with respect to the individual phases, and that's what a Berry phase is. And so if we now take the density of points going in the limit to infinite density and convert this to an integral, I have some parameter lambda, which I imagine goes continuously from 0 to 1 as I go around the loop. And I've got u lambda defined as I go around the loop. And this is the Berry phase. This is the continuous analog of the discrete formula that I showed you a moment ago. The derivative acts on the ket, but you often see this written in this symmetric form. It looks like a matrix element of something, but that's misleading because this derivative acts on the ket. And in fact, there's kind of a paradigm change here in that we're used to dealing with quantum mechanics physical observables being expressed as expectation values of one particle operators, and this is really not that. It's something a little bit different. In any case, again, this global phase is gauge invariant. Here the proof goes like this. You imagine that you twist the phase by some beta of lambda as I go around the loop. So I have some initial choice u and some new choice u tilde, and both of them are going to yield the same phase angle phi. That's because in order for this to be a smooth gauge, I need to have that the phase angle is the same for lambda equals 0 and lambda equals 1. And when you plug this u tilde into this formula and take the derivative acts once on the u, and that gives you back the old phi, and it acts once on the beta, and it gives you this piece of the integral, which is just 2 pi times the difference between beta at 1 and beta of 0. So in other words, if beta varies and comes back to itself, then this integer is 0, but if beta evolves by 2 pi, that's also permissible, and then the phase changes by 2 pi, but of course if we interpret the phase as a phase angle between 0 and 2 pi, then phi hasn't changed, and that's the philosophy. We regard phi as a phase angle defined on the unit sphere, and that Berry phase is gauge invariant with respect to the choice of phases as I go along the loop. The integrand here is known as the Berry connection or the Berry potential or sometimes gauge potential. And so the Berry phase can be written as an integral of the Berry potential as I go around the loop. So that's a notation which will be used from time to time going forward. And now Berry curvature. So this is the third Berry quantity. By the way, last time I gave a talk on Berry phases, Michael Berry was in the first row. It was a little daunting, but I think I got through it okay. Berry curvature, the idea is this. You imagine that you have some, let's say, two-parameter space, and I can do a Berry phase around the perimeter, or I can imagine dividing up this region into little squares and doing a Berry phase calculation around every little square. And so if I compute the Berry phase around a small square divided by the area of that small square, that gives me something called Berry curvature. So if I take the continuum limit of that thing, then of course Stokes' theorem just says that if I integrate the Berry curvature over the interior of this patch, that's equal to the Berry phase around the perimeter of the patch. And so this Stokes' theorem is a fundamental part of the understanding of the relation between Berry phase and Berry curvature. If you work out what this Berry curvature is, it actually, since there's basically a derivative in it, again, the Berry potential or the Berry connection has one lambda derivative in it. This one has two, one acting in the bra and one acting in the ket, one with respect to x and one with respect to y. So this is the formula for the Berry curvature. And there's a famous mathematical theorem that says that if you integrate the Berry curvature over some closed manifold, it has to be 2 pi times an integer. That's the Chern theorem. So I haven't talked about electronic structure yet, but I'm going to introduce this example shortly. If I have a two-dimensional insulator, the Brillouin zone is labeled by kx and ky, which go from 2 pi over a, 0 to 2 pi over a, 0 to 2 pi over b. And I can regard that as a 2 torus. And so if I integrate Berry curvature over this 2 torus, that's an example of a closed manifold. And I'm guaranteed that the integral of the Berry curvature has to be 2 pi times a Chern number. And the proof of this, just very briefly, it's one of these proofs where you just divide up your closed surface. Here I've done it for a closed surface, which is the surface of a sphere. You divide up your surface into two regions, A and B. You apply Stokes' theorem to region A, and that's here, and you apply Stokes' theorem to region B. And in both cases, the result has to be equal to the Berry phase around the perimeter, possibly with a discrepancy of 2 pi, because the phases that differ by 2 pi are physically equivalent. And so if you subtract this equation from this equation, it tells you that 0 has to be equal to the integral of the Berry curvature over the entire manifold modulo 2 pi, which is the Chern theorem. So that's the Chern theorem. So it's very general. It applies to any closed manifold, any two-dimensional closed manifold. And there's a famous example of this, which many of you know, which is the case of a spinner in a magnetic field. If you apply a magnetic field to a spinner, there's a spin up and a spin down state with respect to the orientation of the magnetic field, which have higher and lower energies. If you follow the lower energy state, which is the spin up one, as you change the angle of the magnetic field, the nature of the state doesn't depend upon the magnitude of the magnetic field. The splitting does, but the nature of this state does not. And in all these things, what enters is just the state itself and not the Hamiltonian that generated it. And therefore, this Berry phase, as I go around a closed loop in orientation space, only depends upon the loop in orientation space, and the Berry curvature on the surface of the Brillouin zone turns out is exactly a half, and therefore the formula tells you that when you integrate over some path, the Berry phase has to be just 1/2 of the solid angle subtended as you go around the path. And if you do an entire hemisphere, that's 2 pi. Half of 2 pi is pi, so the phase change is pi, which is -1, which is a famous fact that if you rotate a spinner on the block sphere, that you get a minus sign. Okay, so that's all completely general. We can imagine that was for a molecule as I move some coordinates around. Perhaps I should have said that in general, you have to have broken time reversal symmetry to get a non-zero result. So this would typically be for magnetic molecules, not for non-magnetic ones. But crystals are a little bit more interesting because at arbitrary places in the Brillouin zone, you have effectively broken time reversal symmetry, even if the material is non-magnetic. So anyway, here we're making the transition to a two-dimensional electronic structure. So let's imagine for the moment we have a two-dimensional crystal, let's say an insulator, and so our parameters become kx and ky. The wave vectors that label the block states of a particular band of interest. And you know that the block states take the form of some envelope function, e to the I k x, times some underlying cell periodic block function. The uk of x is the cell periodic block function, which has the phase divided out of it from the block function. And all of the geometric properties like Berry phases and Berry curvatures are going to be defined in terms of the cell periodic block function, not the original size. And the reason is that we want to take a derivative like this, du dk. We want to take a derivative of the wave function with respect to k. And the different block functions at different k have different periodic boundary conditions, e to the I k dot x. And so if I take a derivative with respect to k, I'll pull down an x, so I get something which blows up to infinity and is not well defined. But the UKs all belong to the same Hilbert space. They belong to this Hilbert space of truly periodic states on the unit cell, and so there's no problem with taking a wave vector derivative of the UK. And so that's what we do. We define all of the quantities that I just talked about in terms of derivatives with respect to wave vector of the cell periodic block functions. This is A here is a Cartesian index in 2 dimensions running over x and y, but I think I've written this in 3 dimensions here. Yeah, this is in 3 dimensions. So this is the Berry connection. Since I can take derivatives in x, y, or z, it's actually a vector. Here I've written it in vector notation. Here I've written it in component notation. So these notations are just different notations for the same thing. The Berry curvature, I didn't mention this earlier, but what it really is the curl of the Berry connection. That's written in a vector form like this. The Berry curvature is the curl of the Berry connection, and the Berry curvature, when you work out what that generates, when you apply the extra derivative to the Berry connection, you get this form that I wrote before. This is the form in a component notation where I use a 2-component index on the Berry connection, on the Berry curvature. So this is a Berry curvature tensor notation. This is the Berry curvature vector notation. And the Berry curvature tensor is an antisymmetric 3x3 tensor. So it has 3 independent elements. So you do the usual trick of going back and forth between expressing. So I will change language from various places between expressing the Berry curvature as a 2-component tensor or as a vector when we're working in 3 dimensions. When you're working in a higher dimension, you usually use the component notation. Okay, and there's a famous analogy here to the electromagnetic vector potential A and the magnetic field B, which of course are related in this way. So here, these quantities are defined in real space. These quantities are defined in reciprocal space. The derivative is a real space gradient. This is a k-space gradient. But there's a close analogy between these two things. And so that's the sense in which the Berry potential is sometimes called the gauge field in this context. And you can think of this analogy. So, for example, it will turn out that Weyl points look like magnetic monopoles and so on. Okay, so let's talk about a little bit of physics that relates to transport theory, which I think is the direction that we want to go this week. So let's suppose I have a 2-dimensional metal, and I want broken time reversal, so it's a ferromagnetic metal, and it has some Fermi C with some Fermi surface is the loop here, and since it's in 2 dimensions, I'll just talk about the z component of Berry curvature, which is the same as omega xy, the Berry curvature in the plane. Here's the formula for it again. And if I integrate that Berry curvature over the Fermi C and multiply by e squared over h, some universal constant, I get the anomalous Hall conductivity. So I'm going to do a little diversion in a moment to tell you about the anomalous Hall conductivity. This is the Karplus-Luttinger intrinsic part of the anomalous Hall conductivity. Let's see, I'm not sure what I wanted to say, how much of this I wanted to say here. Let me come back and I'll show that slide again and talk about it more. Anomalous Hall effect. So let me do this very quickly. I think people know this. The ordinary Hall effect, you measure a transverse conductivity. You either apply a current and measure a voltage in the transverse direction, or vice versa. For a non-magnetic material in the presence of a magnetic field. That's the ordinary Hall effect. The quantum Hall effect was observed, of course, almost 50 years ago, I guess, in two-dimensional inversion layer, electron gas inversion layers. If you put the Fermi level between Landau levels, then you get a quantized Hall conductivity in units of E squared over H. Here it's, for this figure, it's in the second quantized, it's in the second gap between Landau levels. And of course, there's a plateau in the transverse conductivity, and the longitudinal conductivity, which is green, goes to 0. And so that's the quantum Hall effect. In a ferromagnetic sample, there's something called the anomalous Hall effect, where you simply replace the external magnetic field by the fact that the material itself is ferromagnetic. So for example, if you have an iron sample with a net magnetization and you do this Hall effect, you'll measure the anomalous Hall conductivity. And what I'm telling you here is that the anomalous Hall conductivity that you would measure in this two-dimensional metallic sample has a contribution that is given by this integral of the Berry curvature over the Fermi sea. So I'll explain a little bit more about this. I want to emphasize the fact that this is only the intrinsic part. That is to say, this is for a perfectly clean material where I haven't included any scattering, I haven't included any relaxation time effects. It's merely the fact that the electric field perturbs the underlying Bloch wave functions in such a way as to generate a transverse conductivity. And so it's not it was quite controversial actually after Karplus and Luttinger initially proposed this in 1969. I took this this piece of a presentation from a little review by Patrick Bruno. But the point is that in those days they wrote this down using the Green-Kubo formalism as a linear response property, and it looks like this. And let me just explain how it gets into the form of a Berry curvature. So in the linear response, you have these matrix elements of the velocity operator. But what you can show is that the velocity operator matrix element between Hamiltonian eigenstates is related to that of the derivative operator acting on the ket in this way. So when you replace the velocity operator matrix elements by these, you get energy denominators that kill the energy denominators. The energy denominators go away, and you just get this formula that says that I integrate the Berry curvature F is the occupation function, so over the occupied portion of the Brillouin zone. So this was quite controversial because, as I said, there's no scattering, there's no relaxation time. It doesn't fit into the usual picture of Boltzmann transport. It's something that gets added on top of that. There will, in addition, be defect contributions, so-called skew scattering and side jump scattering, to the anomalous Hall conductivity, which will dominate in some cases and not others. But here I'm only talking about the intrinsic contribution. So at this point, it's worth stopping to emphasize the symmetries. So in the Brillouin zone, the Berry curvature does not flip sign under inversion. Of course, the wave vector does flip sign. So the Berry curvature at one point and an image point in the two-dimensional or three-dimensional Brillouin zone are the same. So that's like a magnetic moment. Inversion doesn't flip the sign of magnetic moment. And this is also like a magnetic moment. Time reversal does flip the sign of a magnetic moment, and it flips the sign of the Berry curvature. So what this means is that, for example, if I have something like copper, which is non-magnetic and centrosymmetric, then the Berry curvature is identically zero everywhere in the Brillouin zone. And so the tradition of ignoring the Berry curvature is perfectly well justified in a case like that. if I have something that's non-magnetic but not centrosymmetric, let's say gallium arsenide, then what happens is that the Berry curvature at one point and another point in the Brillouin zone are equal and opposite. And when you integrate over the full Brillouin zone, or when you integrate over the Fermi C in a metal, you always get zero. But you have the possibility of disturbing that balance by some kind of optics or transport or driving. And so we'll talk about that a little bit later. And so, and then in the case of a ferromagnet, whether it's centrosymmetric or not, the integral of the Berry curvature over the Brillouin zone does not have to vanish by symmetry. And therefore, in general, you'll have a non-zero anomalous Hall conductivity in the case of a ferromagnet. Okay, so here again, this is in the case of a metal. If I imagine going from the case of a metal to the case of an insulator by expanding the Fermi surface until it fills the entire two-dimensional Brillouin zone, and now the Fermi C, in some sense, is the entire band spanning the entire two-dimensional Brillouin zone, and I integrate the Berry curvature over this two-dimensional Brillouin zone, then remember our Chern theorem that says that when I integrate the Berry curvature over the Brillouin zone, it's 2 pi times an integer. So the result is going to be that this integral will be 2 pi times the Chern number. So the 2 pi's cancel, and the result is that this is e squared over h times the Chern number. So, in 99.9% of all two-dimensional insulators, the Chern number is going to be 0, certainly if it's a time reversal invariant insulator. But if it's a ferromagnetic insulator, then you have a chance that this Chern number could be +1 or -2, and in that case, the anomalous Hall conductivity is quantized to be 1 or -2 times e squared over h, and you get the famous quantum anomalous Hall insulator state. QAH will be the acronym that I used, also known as a Chern insulator to some. And so the discovery of the Chern insulator, quantum anomalous Hall insulator state in 2013 famously completes this, this tableau of Hall effects, the ones that occur in the non-magnetic systems by an external magnetic field, or that occur in a ferromagnetic sample, either in a metal or in an integer, in an insulator. Okay, so let me tell you a little bit more about this quantum anomalous Hall effect, and the discovery of the experimental system. This story really goes back to a famous paper of Haldane in 1988, in which he wrote down a tight binding model which realizes the quantum anomalous Hall state. It's a simple model involving a honeycomb lattice with two sites that have energies, site energies delta and minus delta, nearest neighbor real hoppings T1, and second neighbor complex hoppings T2 e to the I phi, where phi is a phase angle, which is a parameter of the model. And the system, this is a system of scalar electrons, but the time reversal symmetry is broken by the fact that the hoppings are complex. Of course, the hopping in the opposite direction is the complex conjugate because the Hamiltonian is still Hermitian. But this basically realizes a two-dimensional ferromagnetic system in this simple tight binding language. And what you find is that this model has, in its parameter space, so phi is that phi phase angle. This is the site energy shift divided by the second neighbor hopping strength or something, doesn't matter. So you have a region where the Chern number is 0, but then regions where the Chern number is +1 and -1. And, if you cross this boundary from the region where the Chern number is 0 to the region where the Chern number is 1, what you'll see is that in the two-dimensional band structure, there's some place where the valence and conduction bands come and touch at the boundary and then open again. And when it opens, it's now in the quantum anomalous Hall phase, but there's no change of symmetry between before and after. So by analyzing the symmetry of the system, you can't determine the topology. The topology is something famously in addition. And one way of understanding what the Chern number of the quantum anomalous Hall state is follows from a certain way of looking at the Berry phases as I split up dimensions. So I imagine that I have a two-dimensional insulator where the wave vectors are kx and ky in the Brillouin zone. And I choose one of those, let's say kx, and I fix the value of kx, and then I let ky range from 0 to 2 pi over b. So in other words, I calculate the Berry phase along a string of k points in the vertical direction. I drew it with little dots here because I imagine using the discretized formula, which is what you would do in practice on the computer. But in principle, it's just this integral of the Berry connection in the y direction, along the y direction, as a function of kx. You can switch the roles of kx and ky if you prefer, and you'll see something similar. So what you see is that you plot the Berry phase as a function of kx. Of course, when you leave from the left-hand side to the right-hand side, the Berry phase has to come back to itself because the left-hand side of the Brillouin zone and the right-hand side of the Brillouin zone are really the same thing. But it can vary along as you do this. And of course, I said it has to come back to itself, but there are two ways that it can come back to itself. It can simply come back to itself, or it's also allowed to come back to itself modulo 2 pi. So as you go across the Brillouin zone, this Berry phase is allowed to shift by 2 pi. And of course, it really was only well-defined modulo 2 pi in the first place. So if you like, there's another ghost image up here, which is 2 pi higher, and that goes up, and this one goes. So, but maybe you should just think of this as defined on a unit circle, and as you go across the Brillouin zone, you go once around the unit circle. So it's a winding number. It's the winding number of the Berry phase defined in the y direction as you take kx across the Brillouin zone in the x direction. And that is what this Chern number is. And now you can kind of see how this can't possibly change if you make some distortion of the Hamiltonian that doesn't close the gap. If it doesn't close the gap, then the winding number can't change. At that moment when the gap closes, what happens is that somewhere along here, the Berry phase becomes ill-defined, and then it reconnects, and the Chern number can change. And this is related to the anomalous Hall conductivity in a way that we'll wait until tomorrow for me to really discourse on. But one thing I didn't really explain to you, I will explain tomorrow, is that the Berry phase in the y direction is related to the centers of the Wannier functions in the y direction. And so, and I'll explain what those are. And so as the wave vector changes, the Wannier functions are moving in the y direction, so they carry a current in the y direction. And so if I regard this as a change in the Wannier center position rather than a change of the Berry phase, then it's a little bit more physical. So for example, if I apply an electric field in the x direction, you know that according to Boltzmann transport theory, that applies a force on electron wave packets, and there's a linear in time change of kx. Kx migrates across the Brillouin zone. Well, actually migrates in the opposite direction because electrons are negatively charged, but never mind. And so during that migration, the electrons move in the transverse direction and give a transverse current. And if you work out a simple exercise to work out the result of this picture is that the transverse conductivity that you get is just e squared over h times the Chern number. So I'll explain what Wannier functions are and the Wannier centers in relation to the polarization and current in the next lecture. But so far, this is just kind of a taste of what will come then. Okay, there's another famous thing about the quantum Hall state as well as the quantum anomalous Hall state, which is that at the boundary of such a state, you have chiral edge channels. So that means that you have some metallic channels at the boundary in which there's a possibility of carriers to move, let's say, in the counterclockwise direction, but not in the clockwise direction. That's what's meant by chiral. And the presence of one chiral edge channel corresponds to the fact that the anomalous Hall conductivity is e squared over h, so Chern number of 1. If the Chern number is -2, it means there are two edge channels running in the opposite direction. and so on. And that applies in both cases. And one way to see this in connection with what I just told you, imagine you have some two-dimensional ferromagnetic metal, so it's got broken time reversal symmetry. What I'm trying to illustrate here is a view of material that is actually infinite in this direction and semi-infinite in this direction, and there's a surface in plus y hat direction here. And so along this surface, kx is still a good quantum number, but of course ky is not a good quantum number at the surface. And so if you plot as a function of kx what the projected bulk bands look like, that's this blue hashed region, and then if you include also possible surface states, you may get some states that emerge out of the valence band or conduction band, which are called surface states. And in this case, you may also get a situation like this, where you have a surface state which leaves the valence band and enters the conduction band as you go across the Brillouin zone. Now, this isn't possible if you have time reversal symmetry. If you have time reversal symmetry, the left half and the right half are mirror images of each other in this figure. But if you have a ferromagnetic metal in 2 dimensions and go to the edge and you break the time reversal symmetry and you also don't have some mirror symmetry or something else, then you can get a situation like this. And it turns out that the number of, and so what this is it's the chiral edge channel. There's a state where here the Fermi velocity is to the right because the slope is positive, and there is no state with a Fermi velocity to the left. So carriers on this surface can only move in one direction and not the other direction, and so you have a chiral edge channel. And the connection to the anomalous Hall conductivity, one way to think about this is that if you apply an electric field parallel to the edge, then the transverse conductivity tells you that you get some current flowing towards the edge, and that appears to violate charge conservation. In fact, it would violate charge conservation if there were no chiral edge channels. There were no edge channels crossing the Fermi energy. You'd have electrons accumulating at the surface with nowhere to go. We're really talking about here about ground state physics. So, for example, suppose I have a ribbon that's 100 angstroms wide, and and in this direction 100 angstroms or 1,000 angstroms. I apply an electric field that's weak enough that I don't actually start tunneling electrons out of the system. And so I'm just talking about the ground state of some flake of matter, and so it has to obey, it's a stationary state, and charge densities can't change as a function of time, so you can't have accumulation of charge at the boundary. And so the only way you get out of this is to have a chiral edge state that can suck up the charge that flows to the surface. So if you do a calculation of how the charge that gets flowing to the edge is sucked up by the surface state, you find out that since these edge channels have to come in an integer number, then the anomalous Hall conductivity also has to be an integer anomalous Hall conductivity, because one is needed to exactly compensate the other and rescue charge conservation. So the conservation of charge is an explanation for why this system has to have the chiral boundary state. And this is the simplest example of the famous bulk boundary correspondence in topological systems. I mentioned that this was discovered in 2013, so that's now a decade ago. This was by Guizhou Chang in Jiqun Zhui's group in China, and this was a film of a topological insulator in the bismuth telluride family with some other mixtures in there with chromium doping to make it into a ferromagnet. And in this thin film form, they were able to show that the system behaves as a quantum anomalous Hall insulator. The initial report, the longitudinal conductivity didn't quite get down to 0. 1 here is in units of E squared over H, and the transverse conductivity didn't quite get to 1. It got to 98% of the quantum. But in subsequent work, they found that vanadium doping works better. And now they were able to get 99.98% of the quantum at 25 millikelvin We now have realizations of quantum anomalous Hall states in twisted bilayer graphene and other twisted bilayer systems as well, and there are other layered materials. It would be interesting to look for really high temperature quantum anomalous Hall states. I think the record now is about 10 Kelvin, but in principle, there's no reason why this couldn't be at 100 Kelvin or maybe even room temperature if you want to dream. Well, maybe we should get the room temperature superconductor first, but after we have that, we can look for this. Maybe I'll just stop for a second. I'm about 35 minutes into the talk, and then I'm going to talk about a few other things. But let me just see maybe if there are questions at this point. I could answer some questions because I'm going to generalize things a little bit in the next part. Yes?
One very main question. In the picture that you showed three-dimensional, yes, here. Why the direction of J is perpendicular to the direction of electric field?
Well, so the question is, why is the current perpendicular to the direction of the electric field? Because the anomalous Hall conductivity that we're talking about is always a transverse conductivity. So sigma yx means that you apply an electric field in the x direction and you get a current in the y direction. And it's a dissipationless current for that reason, because the electric field is not was not applying any power, right? The longitudinal resistivity, sigma xx, means you apply an electric field in this direction and you drive a current in this direction, and that's going to heat the sample. But if you can drive a current in the transverse direction, that's the anomalous Hall effect, and that's a dissipationless effect because you don't generate any power by doing that. And so what I'm arguing here is that if you assume that an insulator is allowed to have a transverse conductivity like this, it's obviously not allowed to have a longitudinal conductivity, or it wouldn't be an insulator. And there was some discussion about whether it's really correct to continue to call this an insulator when there is a transverse conductivity, because you can have a current going in it. On the other hand, the gap never closes, and so in that sense, it's still an insulator. So anyway, we continue to call this an insulator, even though there is a situation in which a current is flowing in it. It's a dissipationless current. It's always perpendicular to the electric field. And I'm saying if you have such a situation, the only way it could happen is if there's also an edge channel that can carry away the charge that arrives at the edge. Does that answer the question? The question in the back? So the question is, what do we need to get quantum anomalous Hall states at higher temperatures? Yeah, so what you want is a larger gap. Now, usually these systems depend upon spin-orbit coupling, usually excluding the case of bilayer graphene, where you get spontaneous flux state, basically, and spin-orbit coupling has nothing to do with it. But in the world of spin-orbit driven topological insulators, the gap, in order for the material to be topological, it should be the case that if you turn the spin-orbit coupling from its full value to zero continuously, that a gap will close and then reopen, because by the time you turn the spin-orbit coupling to zero, it can't be topological. And so that means that the gap has to be on the order of the spin-orbit coupling or less. So let's say on the order of 200 millielectron volts or something. So you want to be able to increase that gap as much as possible. You'd like to use heavy atoms in order to have strong spin-orbit coupling. And then it has to be robustly, there has to be a gap across the entire Brillouin zone, and you have to have a material that, the trouble is also the small gap systems tend to have a lot of residual conductivity defects and so on. So there's a lot of technical problems with finding examples. But yes, basically you just want strong spin-orbit coupling that opens a large gap with the kind of band inversion that is needed in order to get a topological state. Yeah, my. Is there an estimation of what the largest gap can be? Well, I think if you assume something like 300 millielectron volts, and you assume the system is perfect, and then you put in the Boltzmann factor, you have to decide, if you want it to be quantized, to how many decimal points do you want it to be quantized. I don't know how much more to say about that. Another question in the back? No. Well, okay. So the wave function, as you vary through space, it's a complex wave function, and it could be real here and imaginary here and so on. And the phases that I'm talking about, well, I'm not going to go all the way back to the beginning. The phases that I'm talking about, when you put in a gauge change, what you're doing is you're taking an entire wave function at wave vector k and multiplying it by, let's say, e to the 2 pi over 5 or something like that, right? So you multiply the entire wave function. So the entire wave function, can't be simply decomposed into real and imaginary parts, and it's not like the Berry curvature only corresponds to the imaginary part. It's like you take this wave function at k and this one at k plus delta k, and you take the inner product. And then you do that with the next one and the next one, and every one of those inner products you have to include both real and imaginary parts, and then you calculate the global phase. Yes?
In the starting, when you told about the Berry phase, so you had a parameter which you were varying around.
Yeah.
But when you went into resolving zone, what was the parameter now?
The parameter is the wave vector. So let's just talk about a one-dimensional crystal for the moment. Excuse me. So let's say I have a one-dimensional insulator. So that means, and the lattice constant is A. So the wave vector k goes from minus pi over a to 0 to pi over a. That's the Brillouin zone. Now, you probably know that sometimes people talk about the extended zone scheme. So, for example, over here, going from pi over a to 2 pi over a to 3 pi over a is the second, extended Brillouin zone. But that's not really a fair accounting, because a wave vector at k and a wave vector at k plus a reciprocal lattice vector, it's not just that the energies are the same, they label the same state. The state is uniquely labeled by a wave vector between minus pi over a and pi over a. And so it's natural to think about the wave vector as living on a unit circle. And so instead of thinking of it as a segment that goes from pi over a to minus pi over a, you think of it as a circle that goes from 0 to pi, and pi over a, and then 2 pi over e. And so I'm defining the Berry phase on that circle. And so then in the two-dimensional case, what I do is ky, I define the Berry phase on the circle in ky, and then I do that as kx goes from 0 to 2 pi over a. But again, both of these are really circles. And so the topological way of thinking about the two-dimensional Brillouin zone is not as a rectangle, it's as a two-torus. And once you think of it as a two-torus, it's a closed manifold, and you can define topology. And so that's the philosophy behind all this topological stuff, is that you have closed manifolds. The three-dimensional Brillouin zone is a circle in X, a circle in Y, and a circle in Z. So it's a three-torus, which, is a little harder to get your imagination working on what a three-torus looks like. But that's the way to define topology, is in terms of these closed manifolds, either a circle, a two-torus, or eventually three-torus and others. Or for that matter, the block sphere is another example. Yes?
Experimentally, if we can change the crystal from this conventional chemistry, do you think Berry phase will catch it?
So say it again, experimentally, if we can what?
We can build the single crystal. Like, this is a Holberg geometry, and now if I can build the single crystal.
You're talking about, you're asking about physical bending? Is that what you said?
Experimentally, if we can make that, so it will affect our Berry curvature or Berry phase contribution?
I don't think I understand. Let's discuss it after, if you don't mind. I don't think I quite got it. Other before we go on. Yes, okay, here and then here.
So, in principle, trying graph can take any integer value, right?
Yes.
Are there any constraints for like green materials? How high can it get?
I've seen, so there's a little industry in the first principles computational community where people invent fictitious materials, hypothetical materials to calculate properties. So you can invent various two-dimensional insulators and compute Chern numbers. And I've seen people come up with numbers like 1, 2, 3. I don't know if I've ever seen someone come up with 4. Mathematically, there's no reason why you can't have 149, but of course, you have to find out. One way of thinking about it is that if you start from a non-topological system and then you perturb the system or gradually take the system through some path that goes to the topological state, you're going to have band closures along the way, which increase the Chern number by 1 or maybe by 2 if there's some degeneracy. And so there's not just one band inversion, but 2 or 3 band inversions that have to occur in order to get there, so it becomes more and more difficult. I guess that's the way to say why the number tends to be small, but I don't think there's any general principle. And yes?
I just have a minor question about naming. There's some discourse in various articles about whether or not there's a difference between what's called the Zach phase and the Berry phase.
Yes.
Just clarify really briefly what might be the difference.
Okay, the question is about the Zach phase and the Berry phase. And I mentioned that Michael Berry was in the front of the audience at the last talk I gave, and Joshua Zach was in the back. So the Zach phase applies to the one-dimensional Brillouin zone of an electronic structure problem. And so, so he understood that that when you take the wave vector across the Brillouin zone, you can define a Berry phase, and that thing has come to be known as the Zach phase. And in fact, he also understood the symmetry properties of that thing. If there's a mirror symmetry, then the Berry phase, the Zach phase has to be 0 or pi or whatever. The Berry phase is basically just the same thing, but generalized to any other context. So, for example, if you follow if you do the integral around the boundary of the Fermi sea, that's the Berry phase. Or if you have a molecule and you displace some atoms and come back to yourself, that's a Berry phase. So the Berry phase is the more general term. The Zach phase is the specific term, and so I could have used, for much of my talk, I could have been using the language of Zach phase, because in fact, those string Berry phases that I was calculating were Zach phases. The Zach phase is the electronic structure application of the Berry phase. Thanks for that question. Okay, let me, good, I'm glad I did that. And then, I'll try to leave a little more time for questions at the end, but I think I started 10 minutes late, so I'll try to be ready for for Jen to take over at 10 after. Yeah, no, that's what I'm planning on taking the 10 minutes. Okay, so I wanted to talk a little bit about the nonlinear Hall effect. I think this will come up later and maybe in the hands-on. No? Maybe not. So I just wanted to mention about the nonlinear Hall effect as an example where by perturbing the system, you can make something that had no net Berry curvature have a net Berry curvature. And so let's consider some non-magnetic but non-centrosymmetric metal, some polar metal, perhaps. And so the symmetry principles that I told you about before tell you that the Berry curvature at k and minus k are equal and opposite. And so when you integrate the Berry curvature over the Fermi sea, you're going to get 0 because of a cancellation between k and minus k. That's what it says here. But now let's combine this with Boltzmann transport theory. Boltzmann transport theory says that if I have a system, I apply an electric field in the x direction. If I think of the Fermi sea made up of wave packets, those wave packets will drift in the kx direction in such a way that the Fermi sea gets displaced. Then there's a scattering time at which carriers at the right side of the Fermi sea get scattered back to the left-hand side, and you establish a dynamic equilibrium in such a way that the Fermi C is shifted a little bit in reciprocal space by an amount that is proportional to tau is the scattering time, the relaxation time that's in your Boltzmann transport theory. And once you've shifted the Fermi surface, then you don't necessarily have a cancellation between k and minus k anymore, because there are states near the Fermi surface that are populated on the right-hand side and not populated on the left-hand side. And so you disrupt the balance, and you end up generating a net Berry curvature. And if you integrate that net Berry curvature over the Brillouin zone, you get an anomalous Hall conductivity. So this says that in the presence of an applied electric field, steady state system, there is an anomalous Hall conductivity. That says that if you come along with an additional electric field, you'll measure an anomalous Hall conductivity. So this theory of this was famously worked out by Soderman and Fu in 2015, and actually they did a proper time-dependent derivation of this. So you imagine that the electric field is applied at frequency omega, both of the electric fields, both the one that, well, in my language, the one that was displacing the Fermi surface and the one that was creating the anomalous Hall conductivity, are applied at frequency omega. And since I have two powers of electric field, this is a nonlinear effect. And so there's a current which is proportional to the product of these currents. The star here means that this is at e to the I omega t, and this is at e to the minus I omega t. And you know, it has to be antisymmetric in components B and C, obviously. And actually, there are two effects here. There's a static effect, which is that there's a static current generated by this, which is essentially what I was just telling you, that when the electric field is to the right, I get a net Berry curvature, which is positive, and I get a transverse current this way. And then when the electric field is this way, I get a net Berry curvature, which flips sign. If it hadn't flipped sign, the current would be this way, but it's this way, and so I get a net effect. This thing is the 2 omega, so whenever you have a nonlinear effect, you also have a 2 omega response. So there's also possibility of observing a current at 2 omega, which should be related to the same underlying material property. And the material property, so of course tau is the relaxation time, omega is the frequency, but the material property that matters is this integral over here. You can either write it as a Fermi surface integral, as this is the derivative of the Fermi occupation function. So this is essentially an integral on the Fermi surface of the Berry curvature dipole, or you can write it as an integral over the Fermi C of the k vector derivative of the Berry curvature. In Soderman and Fu, they introduced this notation DAB for this, and it's really effectively a third-rank tensor, although it doesn't look like it, but we're representing the second-rank tensor Berry curvature in the pseudo-vector notation, so it's a nonlinear response. Oh, it's funny. I thought I added a picture here. It doesn't matter. This is from a paper that we wrote on molybdenum ditelluride a few years ago, where postdoc Shobit Singh and we calculated the Berry curvature on the Fermi surface of this material, well, everywhere inside the Brillouin zone as well. I think we did the calculation using both the Berry Fermi C and the Fermi surface implementation. And so the color coding here doesn't come out very well on this slide, but the opposite colors are the two signs of Berry curvature, and this is for the X and Y components of the Berry curvature that are generated, and this is our calculation of those D coefficients. And so the relevant value is really at the Fermi level, but as an experiment, as a theoretical experiment, we varied the Fermi level over a range from 200 to minus 200 millivolts to see how much variation there is. And as you do that, of course, you change the location of the Fermi surface and you change the nonlinear anomalous Hall conductivity.
I have a question.
Yeah.
Why dxy and dyx there are not related by symmetry?
Because there is no simple interchange of indices here. This thing is the very curvature in pseudo-vector notation, and so it's really a second-rank tensor already, and so I'm taking a derivative of that second-rank tensor. So I don't think it's profitable to try to go through the symmetry analysis in front of you here, but what's true is that phi is antisymmetric under B and C. But then there's some reorganization of indices that happens here, and it's not true that CAB is antisymmetric under A and B. They're just different, at least for this material. For some other material, they might be the same. Yeah?
Do I need time reversal, or can I have it?
You don't need time reversal. You don't need broken time reversal for this. So the point here is that you start with a non-magnetic material. This example that we use, the TMS23, has a transition metal, but it's not magnetic. And the point is that when you apply the electric field, that drives the current, and the current breaks time reversal symmetry. So it's the transport effect that breaks time reversal symmetry in a material which is non-magnetic. Now, you can also have this effect in a system that already has broken time reversal symmetry, but in that case, the linear effect probably far dominates the second order effect, and it would be harder to observe. So it's more interesting that this happens in a non-magnetic material. Yeah?
How can I understand the shape of these characters? Normally, as you said before, normally if you have your own cell, it's just a force, no?
Yeah, well, okay, so this is a complicated material, and if you plot the band structure in the three-dimensional Brillouin zone, there are several places in the Brillouin zone where the conduction band and the valence band get close to each other, and so it's not a simple picture. And so you just, it's a situation where you have to do a first principles calculation in detail, where you follow the band structure, calculate the Berry curvature at each point in the band structure, and it's just very complicated. Okay, let me finish. I think I can do this in 5 minutes. I just wanted to give you a little picture that's a little different from what I've been talking about, that may be more related to transport theory, which is, I've talked about wave packets under my breath a couple of times. So let's imagine that I make a wave packet in a crystalline material for an electron, and the wave packet is going to be built out of block states with some envelope function. So the envelope function is localized enough in reciprocal space so that it has a well-defined center Kc in reciprocal space, but it's also localized enough in real space that it has a well-defined center Rc in real space. And then, of course, this thing in general is a complex wave function, and a complex wave function can have current, so there could, for example, be a circulating current in this little wave packet, or perhaps not, depending upon whether the system is magnetic or whether I'm in a part of the Brillouin zone where the symmetry is low enough. So in most textbooks, you'll find the Boltzmann transport theory derived in terms of equations that look like this. It says that the position of the wave packet, time derivative, which is the velocity of the wave packet, is given by the group velocity. This is the group velocity, the derivative of the electron energy with respect to wave vector. And the wave vector changes in time according to the force applied, which is the electric and magnetic field, where the magnetic field acts on the group velocity. But there's a missing term in this, famously the anomalous velocity term. There's a good review of this from 2010 by Xiao Chang and Yu that I recommend, that talks about the anomalous velocity and the role that it plays in various physical phenomena. But this is basically what's needed. It's funny, I thought I added something here too. This is what's needed in order to understand the anomalous Hall conductivity in the context, in this context. Because if I apply an electric field in the x direction, I get a kx dot, I get a time variation of kx in the x direction, and that crossed into the Berry curvature xy gives me a velocity in the y direction. And so that gives rise to the anomalous Hall conductivity if it doesn't get canceled out as I integrate over the Brillouin zone. Okay, and so if I oh yeah, okay. I'm sorry. I thought I was missing out the anomalous velocity term, but I wrote this as the group velocity on the next slide. So here's the group velocity. There's the anomalous velocity. So these are the equations that include the anomalous velocity term. But here you've got, for example, k dot on the right-hand side and on the left-hand side in these equations, and the same with r dot. And if you systematically move all the k dots and r dots to the left, you can rewrite the equations like this. And this is an interesting form because on the left-hand side you get this quantity in parentheses, 1 plus E over h bar c times the inner product of the external magnetic field and the Berry curvature. So this says that if there's both an external magnetic field present and a Berry curvature present, and they're not orthogonal to each other, you get an interesting effect. And what this effect is it's really a renormalization of the density of states. So, you know, the density of states in K-space, so density of states means number of states per K-space volume per real space volume is normally just 2 pi to the minus 3. But if there's a Berry curvature and an external magnetic field present, you get this modification of the density of states factor. And again, I recommend the review article that presents this in a very transparent fashion. Not exactly the way I presented it here, but these are the equations that you get if you consistently move all the r dots and the k dots to the left. And I want to mention also, I mentioned that this wave packet in general is a complex quantity, and there may be some circulating current. And if you compute the circulating current, that's the orbital magnetic moment of the wave packet. And it takes the form that looks, if you ignore this h minus e in the center, it's a Berry curvature, but it has the Hamiltonian minus the band energy sandwiched in between, and that's the orbital magnetic moment of a wave packet. And so I think this is my last slide. The way that I'd say a modern view of electrons in a crystal and in the vicinity of the Fermi surface, if it's a metal, what do you need to know about the wave functions? You don't need detailed information about everything about the wave function. You need to know the band energy. You need to know, in general, the spin moment and the orbital moment. The orbital moment is the one I was just talking about here. It's a different notation here. I'm calling it mu. And the Berry curvature as a function of wave vector k, either at the Fermi energy or often you need wave vector derivatives of these quantities. So, for example, of course, the wave vector derivative of the energy is the group velocity. You need that. And for the Berry curvature dipole moment, for the nonlinear Hall effect, you need a derivative of the, well, depending upon how you write it, you may need a derivative of the Berry curvature and so on. So I want to be a proponent of thinking about, the most general Fermi liquid theory. You're given not just the band energy E, but you also need this other information about electrons at the Fermi energy, or in general at different points in the Brillouin zone. So so that's the end of the talk. These are the topics that I covered. I think I had a lot of questions during. Maybe if there's one or two pressing questions at this point, but otherwise I should turn it over to Jen. And of course I'll be around if people want to catch me. Okay, good.